This is the fourth lecture from the series Making Sense of QFT. The title is Weinberg's Fields. Here is the outline of today's talk. First, we'll construct a Hilbert space with variable number of particles. It's called the Fock space. Creation and annihilation operators provide a convenient notation for doing calculations in the Fock space. As usual, there is no difficulty in describing non-interacting systems in the Fock space, but the most important and difficult task is to build an interacting representation of the Poincare group there. And this task can be accomplished by doing what I call the Weinberg's trick. It's true that this trick leads to the same quantum field theory as in other textbooks, but the Weinberg's way is truly remarkable because it provides a completely different perspective on the role of particles and fields. We ended our last lecture with the realization that we need a Hilbert space in which states with different particle numbers can coexist. Such a Hilbert space is very well known. It's named Fock space after Soviet theoretical physicist Vladimir Fock. The Fock space is defined simply as a direct sum of all n-particle subspaces. Note that the first term in this sum is a one-dimensional Hilbert space of the vacuum, where numbers of particles of each type are zero. If we make a bold assumption that all physical systems are just collections of interacting particles, then we have to realize that quantum states of all such systems can be found in the Fock space that we just constructed. The states of a single electron and the largest galaxy are vectors in the same Fock space. There are also vectors that are superpositions of states with different numbers of particles. For example, a superposition of excited atom and the same atom in the ground state plus a photon. So in the Fock space we can describe naturally the light emission and absorption as well as all other processes involving creation and annihilation of particles. Now, according to the Wigner-Dirac prescription, we have to define a unitary representation of the Poincare group in the Fock space. We already know that each sector with J particles has a natural non-interacting representation of the Poincare group. Then we can just form a direct sum of such representations and obtain the non-interacting representation in the entire Fock space. The good news is that this representation provides a complete description of systems with any number of non-interacting particles. But from the physical point of view, this is not very interesting. But this representation will play a very important role in Weinberg's formalism. So we will spend some more time with it. In principle, it's not difficult to find out the 10 generators of this representation. For example, the total non-interacting Hamiltonian has a well-defined form in each sector. In the vacuum subspace, the energy is zero. In the one electron sector, we get the usual function of momentum. In the two electron sector, we have the sum of kinetic energies of the two electrons, and so on, to infinity. But this is a theoretical nightmare. You cannot do any sensible calculations with this notation. Creation and annihilation operators will come to our rescue. Creation operator is designed to add one particle with certain momentum and spin to each vector in the Fock space. For example, if we take the vacuum vector and keep applying various creation operators to it, we can eventually construct states of all possible systems in nature. Annihilation operators remove a particle from the system if such a particle state was present there. Otherwise, the result is zero. In calculations, it's very convenient to use anti-commutators of fermion creation annihilation operators and commutators of boson operators. I have to stress that creation and annihilation operators are purely mathematical objects. They do not describe any physical process. For example, it's impossible to create an electron out of nowhere, because by doing so we'll violate all kinds of conservation laws, including the charge conservation law. The true reason for introducing creation and annihilation operators is that they provide a convenient notation for writing real physical operators. For example, I'll claim that the operator in the parentheses represents the number of electrons with momentum p and spin sigma. Indeed, let us act by this operator on an arbitrary state vector psi. If the electron state p sigma was present in the big psi, then the annihilation operator on the right will remove this electron state, and the creation operator on the left will recreate the electron with the same properties. As a result, the full state vector gets multiplied by 1, or by the number of electrons with momentum spin p sigma. If, on the other hand, there were no electrons with momentum spin p sigma, then the result is 0, again confirming our interpretation of this operator. Note that due to the Pauli exclusion principle, the number of p sigma electrons cannot be greater than 1. Next, it's easy to obtain the operator of the total number of electrons in the system. We just integrate the p sigma number operators over all momenta and sum them over two spin projections. Then, by inserting in the integral the one electron energy, we obtain the electron part of the total energy operator for non-interacting electrons. This new expression is valid in all sectors of the Fock space. Obviously, it's much more convenient for calculations. That's the real power of the creation and annihilation operators. Similar formulas exist for other 9 non-interacting Poincare generators. And once we have all 10 generators, it's not difficult to build the full unitary representation of the entire group. In this notation, I took into account that each Poincare transformation can be decomposed into two components. First is a Lorentz subgroup transformation, which is a combination of a rotation and a boost, and denoted by the symbol lambda here. And second is a four-dimensional translation, which is denoted by A tilde. So, now we obtained a complete description for any number of non-interacting particles in a convenient notation. But surely we are not interested in non-interacting particles. We want to know how they interact with each other. That's the whole point of physics. According to our initial plan, we have to construct an instant form representation of the Poincare-Lie algebra. So the next important step is to get expressions for interaction operators V and Z through creation and annihilation operators. Isn't it remarkable that all physics now reduced to the construction of only four operators, V and Z? But this is a very challenging mathematical problem because we have to satisfy a large number of Poincaré commutators. Weinberg suggested an ingenious method for solving this problem. His construction is done in several steps. First, assume that we somehow managed to build an operator function V that depends on four variables, which we will name t, x, y, and z. We will call this function the potential energy density. To each value of its arguments, the function supplies an operator in the Fock space with the following properties. If we transform this operator by unitary operators from our non-interacting representation, then function v changes as a four scalar. This means that only the argument of the function is affected by the combination of Lorentz transformation and four translation. The other required property of V is that it commutes with itself at space-like intervals. In other words, the commutator is zero at equal times and non-equal space coordinates. The theorem proved by Steven Weinberg claims that if such an operator function is found, then interacting Hamiltonian and boost can be constructed by the following simple formulas. All necessary commutators will be satisfied. For a proof, see Appendix E1 in the volume 2 of my book. The next question is how to build the operator function V with these properties. And here goes the second part of Weinberg's method, where he introduced quantum fields. Weinberg says, suppose that for each particle-antiparticle species we found a multi-component operator function which depends on the same four arguments t, x, y, and z and has the following properties. First, it's a linear function of creation and annihilation operators. Second, it has the following transformation law with respect to the action of the non-interacting representation u sub 0. Here, d, alpha, beta are matrices of some finite dimensional representation of the Lorentz subgroup. For fermion quantum fields, we require these anticommutators. And for boson quantum fields, we require these commutators. Then Weinberg proved that the required potential energy density operator can be built as a product of several such quantum fields at the same space-time points. This construction may look complicated to you now, but if you compare it with all other approaches for formulating Poincaré invariant theories, you will be struck by its extreme simplicity and beauty. More details can be found in Weinberg's textbook and in the second volume of my book. So far, I showed you a general scheme for constructing a quantum field theory. Now is the time to look at a specific example. This is quantum electrodynamics. Let us try to build the relativistically invariant theory of interacting electrons, positrons, and photons. As we already know, first we have to construct the electron-positron quantum field as a special linear combination of electron and positron creation and annihilation operators, which transform in a certain way and has predefined anticommutator relations. In his book, Weinberg proved that the only way to satisfy all these requirements is to define the quantum fields as shown here. Here A are annihilation operators for electrons, B dagger are creation operators for positrons, U, A, and VA are specially selected four-component numerical functions. After summation over two spin components and integration over momentum, we obtain a four-component operator functions defined on the Minkowski spacetime. This is the electron-positron quantum field. Similarly, one defines a four-component photon quantum field. As a photon is its own antiparticle, here we have both annihilation and creation operator of the same particle present in the field. In fact, I did a bit of cheating here because it appears that the photon quantum field does not transform exactly as a four-vector function. There are some complications involving gauges, additional terms in the Hamiltonian, etc. But the general idea of the Weinberg method still works even in the case of QED. So we will skip these important details. The next step is to combine the above fields in a product with specially selected coefficients that are called Dirac's gamma. Note that all terms on the right-hand side are multi-component vectors and matrices. The indices and summation signs were suppressed for brevity. We are not going to seek any physical interpretation of this expression. For us, its main value is in the fact that it is the simplest possible product of quantum fields that satisfies all required transformation laws and commutators that were defined earlier. Next, using Weinberg's prescription, we set time variable to 0, integrate the potential energy density over spatial coordinates, and add the resulting operators as interactions in the Hamiltonian and boost operators. Thus we get the desired 10 non-trivial generators that satisfy the commutation relations of the Poincaré-Lie algebra. Therefore, we reached our goal. We have a complete interacting relativistically invariant theory in the Fock space. Congratulations, everybody. This means that the physics part of our work is done. The rest of our job is just extracting measurable predictions by performing calculations using well-known quantum mechanical formulas. Now we should be able to answer any question related to the physics of charged particles and how they interact with light. Technically, these calculations could be highly non-trivial, but hopefully there are no more fundamental puzzles to be solved. I say hopefully because, as we will see later, there are two serious obstacles that we have to overcome before we get a fully satisfactory theory. First, we have to solve the problem of renormalization. And second, we'll have to perform the so-called dressing. Solving these problems will occupy us for next several lectures. I would like to conclude this slide with observation that Weinberg's method has led us to the same quantum field theory as in all other textbooks. But the path that we traveled was, in my humble opinion, much more enjoyable. We started from undisputable facts, the Poincaré group of inertial transformations and its representation by unitary operators in the Hilbert space of the system. Then we figured out the existence of special systems, elementary particles, and postulated that all other systems are just groups of particles interacting with each other. If we do not limit ourselves with fixed number of particles, we arrive naturally to the concept of the Fock space. Then the main mathematical problem is to build a non-trivial unitary representation of the Poincare group in the Fock space. Presently, there is only one regular way to achieve this construction. This way involves Weinberg's fields and potential energy density operator. Now you can better appreciate the comparison between two interpretations of QFT that I presented in my first lecture. Let me now say a few words about the physical interpretation of what we just did. First, one can prove explicitly that the electron-positron quantum fields satisfies the Dirac equation. In many textbooks, you can find statements to the effect that this quantum field can be interpreted as some kind of a second quantized electron wave function, and that Dirac equation is a relativistic analog of the Schrödinger equation. I would strongly advise you not to use these interpretations. Quantum fields and wave functions have nothing in common, except probably for the misleading notation in which both these objects are denoted by the same Greek letter psi. Indeed, electron-positron quantum field has 4 components, while electron or positron wave function has only 2 components, spin up and spin down. Quantum field does not have probabilistic interpretation. And Poincare transformations of quantum fields are completely different from transformations of Wigner's wave function. So I would advise you not to regard Dirac equation as a relativistic analog of the Schrödinger equation. It is true that if you apply Dirac equation to the hydrogen atom, you get a very good approximation for the energy spectrum. But I think this is just a coincidence. In future lectures, we'll see how one can describe the relativistic spectrum of hydrogen, including the lamp shift, without resorting to the Dirac equation. Let me now summarize my conclusions. Quantum fields are just auxiliary mathematical tools similar to annihilation and creation operators. Quantum fields are needed only for one purpose, its construction of the potential energy density operator. All other tasks can be accomplished without resorting to fields. Currently, there is no other regular method to construct a non-trivial representation of the Poincare group in the Fock space. All existing quantum field theories are constructed by the same or similar prescriptions. However, there is also no proof that field theory is the only way to build quantum relativistic interactions in the Fock space. And we will see in future lectures that other possibilities do exist. Let me say a few final words about physical interpretation of QFT. When we wrote expressions for quantum fields and potential energy densities, we silently assumed that their arguments are related to the time and position components. But if you think about it, you'll realize that this interpretation was forced upon us only by the misleading notation that used familiar letters T, X, Y, and Z. As we mentioned previously, fields and energy densities are good only for constructing interactions in the Hamiltonian and boost. But in these interaction operators, the t argument is set to 0, and x, y, z components are just dummy integration variables. So I would prefer not to assign any physical meaning to the arguments of quantum fields. This does not mean that our theory has nothing to say about space-time properties of systems. We still have physical time as a parameter of time shifts in the Poincare group, and there are particle position operators in each sector of the Fock space. So we have everything we need to study how positions of particles depend on time. So see you next time. Thank you.